Thank you very much. I'm really grateful to be invited to talk in this seminar. What I want to talk today is about a very long project that we've had with Emmanuel Jacob and Peter Mörters. And hopefully we uploaded the last piece of this project maybe a couple of months ago to the archive. And it's very long, so I don't expect it to be published anytime soon. And this is a talk I've given several times now, and it's built on top of the previous ones, and we keep adding results. So I'm really sorry if time is a little short. What I will do today is I will give some preambles to the problem, to motivate what is it that we want to study. And then I'm going to give the model that we study and the first works that we did. That was, I'd say, maybe 6-7 years ago, and the new results that are just uploaded a couple of months ago. So I will begin by talking about the contact process. So to anyone of you who is not familiar to the contact process, it's a particle system. What we take is a connected and locally finite network. For instance, in here we have a network with several vertices, which is finite, but of course the process can be defined on an infinite network. And what we do is we will look at the configurations of the network in which to each vertex we assign it to be either healthy with a 0 or infected with a 1. And it can be done with colors as well, so I will do that just for visual effects. And what we are going to do is we're going to paint blue every single vertex that is healthy and red each vertex that is infected. And the dynamic of this process is the following. We give some local rules. So each vertex that is infected, right? So each one of these red vertices will become healthy at rate 1. Right? And each vertex that is healthy will become infected at a rate which is proportional to the amount of infected neighbors. So for instance, this one is infected at rate this lambda. This one is infected at rate 2 lambda because it has 2 infected neighbors. This one has 2 infected neighbors, so 2 lambda. Here is infected at just at rate lambda. And this one has no infected neighbors, so it's infected at rate 0 times lambda. And it's important that this parameter lambda here will determine how strong the infection is. We call it the infection rate, right? And it measures how strongly the infection propagates. Now, the configuration in which everyone is healthy is absorbing because there is everyone is becoming infected at rate 0 times lambda, so you cannot exit this configuration. And we call the heating of this configuration the extinction of the infection. Of course, everyone who works with the contact process is always on the side of the infection instead of the term being on the side of the population. So we talk about the extinction and survival, and we always root for the survival of the infection. And we were going to say that the infection is strong if the infection stays away from extinction, from this configuration. Now, of course, if the network is infinite, this is possible, right? And we are going to say that in this case, the probability of never reaching extinction is larger than 0. Then we are going to say that the infection is strong. However, if the network is finite, of course, this is a Markov process, right, with a finite amount of states, and it's going to eventually reach this the absorbing state. So there's it makes no sense to try to ask for this, but instead we're going to say that the infection is strong if the extinction time is very large. So if we are just going to be very far away from extinction for a very long time. Okay, now if the infection rate is very, very large, much larger than the recovery rate, then we're going to say that the propagation effect is much larger than the recovery, and then we expect it to see survival of the infection. However, if the infection rate is much smaller than the recovery rate, then of course everyone is recovering much faster than the infection is propagating. There should be an extinction. And the very first results that came for the contact process include this one, in which if you take any infinite network, then what you're going to see is there's going to be a critical parameter, lambda c, which depends on the network, such that if you start from a finite configuration, right, then for infections stronger than this minimum infection rate, then you're going to see is that the infection is strong, meaning that there is a chance for the infection to never die out, right, to never reach extinction. However, if you are below this critical parameter, then you are certainly going to go to extinction at some point. Now, of course, this is not only the infection not only cares about how long it takes for you to reach infection or if there is a chance or not, there is also some behavior associated to it. If you go to the finite case now, right? So for instance, take the infinite lattice and you cut a very big box and you select one vertex in the middle and you start the infection there. Of course, if the box is very, very big, then this vertex is not going to notice that it is in a finite case. So if you take a parameter lambda, which is much larger than the critical parameter of the infinite lattice, then you're going to see some propagation, right? It's going to start growing and until it reaches the boundary. But by then the infection is out, right? There is like a pandemic, everyone is at home, etc. What is the program for the finite networks, right? How do we study if the network is strong or if it's weak? Then what we're going to take is a sequence of finite networks with the vertex set growing to infinity in size, right? And we're going to ask this sequence of network to converge to some infinite network locally, right? For instance, if you take these finite boxes and you let the size grow to infinity, then these boxes grow locally to the infinite lattice. Now, we run the process on each of these finite networks, starting with everyone infected. And the reason that we start with everyone infected is that if you start with only one vertex infected, then there is some chance that it dies out, right, before it can infect anyone else, and the infection does die out from the very beginning, and we don't want to see that. We want to study what happens with the infection once it reaches some critical size. So we start with everyone infected. Now, with this program in hand, we can give this definition of what is strong and what is weak for the infections. If the infection is weak, then we're going to say that there is fast extinction. And what this means is that the extinction time as a function of, as a sequence, so for each of these finite networks, you take the expected extinction time, then this sequence grows at most polynomially with the amount of vertices of the networks, right? And we're going to say that there is slow extinction if this sequence grows exponentially. Now, of course, because we are starting with everyone infected, right? We are taking this initial condition, then of course the extinction time must grow to infinity. And the reason is that because in order for reaching the extinction configuration, every single vertex needs to recover at least once. And since we're going to take a huge amount of vertices at some point, then this will take some time. So this will convince you that this grows to infinity, but how fast is what determines the strength. Now, there are many results linking the behavior of the process in the finite networks with the infinite networks. For instance, we can take this one from 1988 by Darrett and Liu, in which if you take the finite sized boxes of d dimensions, then this, of course, this grows to the infinite lattice. Then you see a phase transition between fast extinction and slow extinction at exactly the critical parameter of the infinite lattice. And there is another result, more recent, from 2017 by Lally and Su, in which if you take the random deregular network, then you observe a phase transition at exactly the critical parameter of the DRE infinite tree, which is the local limit of these random deregular networks. Okay, so that is for the contact process. Now we have to talk about scale-free networks, which is another ingredient of this talk. So a scale-free network is a network in which the fraction of degree k vertices, right, vertices of degree k, decreases polynomially and not exponentially, right? These are very famous networks. The reason being that they're usually used to model, for instance, social networks, which are very common nowadays. What are the characteristics of these scale-free networks? First, we have a lot of high-degree vertices, which we are going to call them hubs or stars. So you can think of them as influencers in these social networks, which have a lot of huge amount of friends, much higher amount of friends than any one of us can make in a lifetime. But to be fair, they are not really real friends. Okay, and we have a lot also high-degree vertices, which are typically close, right? These networks, when in the finite case, are going to be small world. And the smaller the value of tau, this tau is going to be very important, right? It's how heavy the tail is. The smaller the tau, right, the lighter the tail, and the stronger the effect of scale freeness, right? So we're going to see bigger hubs and more frequently. The larger tau, well, we are going to still see a lot of hubs, but not as many. Some examples of these scale-free networks are, for instance, Barabasi-Albert networks, Chung-Lu, Galton-Watson trees with heavy tail offspring. There's many, many of them. Now, one of the key first results is this one. This is by Pimentel. Sorry, I have this button over here covering. No, okay. If you take an infinite tree, right, Galton-Watson tree with heavy tail offspring distribution, which is going to be scale-free, right, in infinite case, then what we're going to see is that the critical parameter of the infection is 0. Right? So what does this mean? It means that it doesn't matter how weak, how feeble the infection is going to be, there's always a chance of an outbreak. The infection is going to become endemic to the population. No matter how harmless, how low infection rate, how lazy the virus is, you have a chance to see an outbreak. And this is very important because, as we were saying, these networks are used to model real world networks. And for instance, you can look at this as a study of viruses on the internet, which is actually one of the first results of the contact network on scale-free networks. The contact process on scale-free networks. Okay, now how does these outbreaks look, right? If you take, for instance, an infection rate, which is very, 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 very small, you can think of outbreaks as everyone becoming infected, but actually no. What you're going to see is that the infection is localized around these hubs for a very, 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 very long time, right? And everyone else is healthy. So this outbreak is not as terrible as it sounds. And the same thing, the same event or the same property happens with the preferential attachment model and heavy tail configuration model. So these are results by Berger and by Chatterjee and Darrett, right? So these are all finite networks. And so the fact that the network studied here is infinite doesn't really play a role on it. Now you can ask, how does this happen, right? How does the infection survive for a long time? Okay, so as we can see in this drawing, what we have to do is to study what happens with the contact process around these hubs, these influencers. So you can think of it as a central vertex with many neighbors, which are not going to be connected just for the sake of simplicity. Okay, so there is a theorem, and this has been proved several times in different contexts, and I'm giving here one of the very first versions of it by Pimentel and another one by Berger in 2005, but this has been proved, I don't know, maybe 6, 7 times. We also did it. you always do it. And what it says is that if you take that the infection rate squared times the degree of the central vertex is larger than some universal constant, then the process survives exponentially long with this formula here, which is lambda squared times d. So if this is large, then you survive exponentially long on this lambda squared d. So how does this happen? For instance, suppose that you take the central vertex is infected and you have some of your neighbors infected, right? And at some point, the central vertex recovers. So what will happen is that, of course, since it has recovered, it's not infecting anymore any of its neighbors. So some of them are going to become healthy again. However, since there are many infected vertices, at least one of them is going to infect the central vertex again. And of course, then the central vertex is going to infect its neighbors again. So this creates a loop that lasts exponentially long. Okay, however, this is not enough. Because when you have a very, very small infection rate, then the stars or these hubs, they become refuges for the infection, but not for a long enough time, because these times are going to be exponential on lambda squared d, right? But you need to have exponential survival on the amount of vertices of the network. So if you have, for instance, let me show you this picture, you have like only a couple of stars, yes, they can survive exponentially long on their degree, but if there is a overwhelming amount of other vertices, then it's not enough to say that it is exponential on the size of the network. Okay, so what is it that will happen? How does this survive exponentially long on the size of the network? Well, you have these stars, right? And they survive exponentially long. And once in a while, these are going to be very rare events, they send some kind of a flare, like a solar flare, like a lightning bolt, just that travels some long distance, L, right? Okay, how much time do you need for you to see one of these very long paths traveled by the infection? It is proportional to lambda to the power minus some constant times this length, right? So you can think of it as lambda to the power minus n. However, on scale-free networks, what I told you before is that these very large degree vertices are not so far away, right? The distance grows sublinearly with d, with the degree. So actually, you have, if you take d very large, right? What you are going to do effectively be doing is to select fewer stars with larger degree, which can survive exponentially long, right? Very, very, very long, but whose distance also grows, but it doesn't grow as fast. So what you're going to be seeing is that if you take d very large, then on the lifetime of this star, this will send flares to the other stars and activate them. So if one of these stars dies out, then the other ones can light it up again. And this creates another loop. And this is why these networks, the contact process, survives exponentially long on this kind of networks. Okay. Now, this is just the last leg of these preambles, right? So I'm going to be focusing on the mean field model, right? So the mean field model is usually the ones that are defined through differential equations, in which you don't consider the geometry of the network. These are usually called compartmental models, and these are where the first epidemiological models considered. The SIR is the most famous one, the first one, the one that started everything, and then you have a lot of variation. And the SIS, which is called the susceptible infected susceptible process, is the one that is associated to the contact process. Okay, so in these mean field models, two agents can infect each other at any time, right? So there's no geometry, so we are going to think of the process running on the complete graph. And the infection rate rescales with the number of agents. So because if you don't rescale the infection rate, then what you're going to see, since you're running on the on the complete graph, and everyone can infect anyone, then this is just going to explode. So you have to rescale it to see something interesting. And in the limit, when the size of the complete graph tends to infinity, what you are left with is just this deterministic ODE, in which you can see here that this is the interaction between infected and non-infected vertices at rate lambda, and this is the recovery rate. Now, in 2001, Pastor Torres and Vespignani wanted to do sort of a mean field version of the contact process on a scale-free network. So how do you do this non-geometry study on trying to replicate the geometry of the scale-free network? So what they did is they wanted to consider vertices of different degrees, and every vertex with a certain degree is going to be connected to a number of vertices of other degrees. So they replicated sort of this equation over here, but an infinite system of ODEs in which each of these rho j stands for the density of vertices of degree j that are infected. And here you have the interaction between the ones that are not infected with the ones that are infected from other degrees. And this k to the 1 minus tau stands for how many vertices of each degree you are connected to. And of course, here you have the recovery. This is not going to be important because I'm not going to do this mean field version, but the exact equation, it's not very important. But just to let you know that they studied this as an infinite system of ODE, and what they found out is that there is this phenomenon of the critical parameter being equal to 0 if and only if this tau is smaller than 3, right? The tau meaning the exponent of the scale-free network. Now, of course, this is curious, right? Because they found something like this. If you plot everything against tau, you have two regions. Before 3, you have this phenomenon in which you have lambda equal to 0, the critical parameter equal to 0. And here you have this is larger than 0, meaning that if you select an infection rate which is sufficiently small, then you're going to see slow extinction, fast extinction. Sorry. And this is in contrast with scale-free networks in which you don't see a difference between regions. You see that for any value of tau, you have this effect of lambda, the critical parameter equal to 0. Okay, so now how can we connect these two results? This is how can these two results, one in the mean field version and one in the static network, live side by side? And what the answer to this, in our case, was using dynamic networks. And I'm going to stop sharing just for a little bit, just so that you can see me. You can see me bigger now? Okay, so what I'm going to show you is something that I made. This is thanks to my wife, who teaches this kind of toys to children. So here you have two vertices that are not connected, and here we have them connected, right? So in the mean field network, on the static network, if you let the velocity go very, very fast, what you see is this, right? So this is what you are effectively seeing in the mean field version, is that like every single time that you want to use the edge, you have to resample it. So it's kind of there, but it's not there. And this is the scaling parameter 1/n that you see in the mean field version. So I'm going to share again. Sorry, this was the didactic moment. Okay. How do I hide this? Okay. Okay, now our model. So we wanted to take a model in which you can define a scale-free network which was sufficiently easy for you to update. So the model is the following. You take the vertex set, the numbers between 1 and n, right? So as we can see here. Let me check how much time do I have. Okay, and then you define connection kernels, right? And we consider two connection kernels. Actually, we consider a little bit more, but these ones are the important ones. This is the configuration model type, right? In which any two vertices, basically when normalized by n, you just take the product raised to this power over here, which is negative. Tau is going to be something larger than 2. And the preferential attachment type, this is this kernel in which you take the minimum between the two vertices raised to this power and the maximum raised to this other power. Both of them are going to be negative. Okay, and the reason that we select these particular kernels is just to replicate the first order statistics of the configuration model and the preferential attachment model. Okay, so you use these kernels. So every two vertex, what you do is to flip a coin, right? And if heads, with this probability, you draw the edge, and if not, then you don't draw anything. And actually, this for these two choices of the kernel, what you obtain is a scale-free network with parameter tau larger than 2. And importantly, the expected degree of any of these vertices, right, is V over n, is the normalized between 0 and 1, raised to this negative power. So if you take vertices which are closer to 1, they are going to be stronger. The expected degree is going to explode, as opposed to the ones closer to n, which is going to be some constant, perhaps 1, perhaps not. Okay, so now we're going to, we want to endow this with some stationary dynamics. Stationary because, of course, we don't want the dynamic to be the reason of change. To be changing the, sorry, we don't want the dynamic to change the statistics of the network, right? You just want to give it motion. So there are two possibilities. Edge updating, in which you select every edge or every possible edge, right, and update at a certain rate, and you just resample it. But this is not going to be something that we will be covering today. And the other one is vertex updating. And vertex updating is just a dynamic in which you select a vertex, right, at a certain rate, and when you select it, you just resample its whole neighborhood. And these dynamics have two parameters, kappa naught, which is going to be the updating rate, and beta, which was something that was over here in the kernels. Actually, this beta is not going to be important. So for instance, here, this is an example of vertex updating. You just select vertex 3, right, which has these two edges, and then you update it. It lost the edge between 3 and 5, and it kept the one between 1 and 3, and you add some new ones, right? Okay, so the first result for this model was by Peter Mörters and Emmanuel Jacob in 2017, in which they found out that for the configuration model type, with vertex updating, right, they found this picture. Now there is this region between 2 and 4, right, in which you have this phenomenon of critical parameter equal to 0, and the other one in which the critical parameter is larger than 0. Of course, this is strange, right, because in the mean field version, the difference between the regions was at 3, and in the static network, right, it wasn't there. So it's not solving anything, it's just adding more. And more interestingly, changing the values of beta or kappa naught, which were the tuning parameters, had absolutely no effect on this picture. Okay, so now a more general dynamic, which was proposed by Renko van der Hotta in one of the talks by Peter Mörters about this process. He suggested the following: why don't you let the vertices or the edges update according to how strong the vertex is? Okay, so this involves including a new parameter, eta, right? And now the vertex updating of each, for vertex updating, the updating rate now depends on the expected degree of the vertex raised to the power eta. And in edge updating, this is just, okay, so you can take a particular edge in vertex updating and figure out the updating rate, which is just the sum of the two kappa x and kappa y. And this is what we decided to be here in the edge updating case. So we wanted edges to update at the same rate here and here. So you have to select this one, this updating rate. But of course, we will not cover edge updating today. Now, how is the behavior of the network in this case? If eta is positive, then the star subnetwork updates extremely fast. So remember that there is a subnetwork of stars in which the contact process is surviving, right? And because the expected degree of these stars is extremely large, then if eta is larger than 0, then the vertex updating, which is the expected degree, which is large, raised to something positive, is huge. So we expect this network to update extremely fast. If this is equal to 0, then we recover the model proposed originally by Mörters and Jacob. And if it is negative, then the star subnetwork starts to freeze, right? The larger the degree, then the more static the vertices are. Okay, now this leads to the first results. I'm really sorry this took so long. This was our first results for the vertex updating with eta positive. And this was a very lucky choice because this was actually the easiest version, the easiest regime. Now, what we want to understand first for the vertex updating with eta positive is what happens to local survival around stars. And what I propose is the following. Please consider one star advancing through time, right? And on this timeline, we're going to mark all the updating events, which are going to be many, right? As I was saying, the stars are updating like crazy, and there are going to be some recovery events. So because the star is initially infected, we don't really care about updating events at first, right? Because you are infected anyway. You don't need friends, right? When everything is good, you can forget about friends. Don't take it from me. Okay, and eventually you are going to see some difficulties. You're going to see a recovery event. And now this star really needs its friends. So now suppose that you just update it and you gain some new vertices. Of course, when you gain some new vertices, you can be very assured that these are going to be all healthy. So you have a brand new set of healthy neighbors. So what you need to survive, to surpass this recovery event, is to first infect some of your vertices, some of your neighbors. So the amount of neighbors that you're going to infect before hitting this recovery event is the total amount of neighbors that you have times lambda, because you are infecting each of them at rate lambda, but this interval of time is of order 1 over kappa x. So you have less time. So this is why this is lambda divided by kappa x. Okay, now you reach the recovery event and the central vertex is healthy. Now it needs to be reinfected before reaching this second updating event. So what it needs is for any of these vertices, its neighbors, to infect it back. So you remember this was the amount of vertices that are infected. Now each of them is going to infect it back at rate lambda. And again, this interval is going to be of order 1 over kappa x. So this is basically something that needs to be large for you to be able to survive. So if this is very much larger than 1, we expect to see local survival. What we managed to prove is that this is true. However, the extinction, the local survival time is no longer exponential. It's only linear with some logarithmic correction. Why is it linear? Well, basically because there is a very large chance that you run into some recovery event which is very close to other updating events. And this is just a problem of the network. And when you hit that, then there is no chance for you to survive. So instead of exponential local survival, we have linear local survival. And the local survival is now lambda squared times the expected degree raised to the power 1 minus 2 eta. And this 1 minus 2 eta is because you have this expected degree and this kappa x squared divided. And this kappa x squared was the expected degree raised to the power eta. Okay, now that we have discussed the local survival, we can look back at what we had before, which were the previous results for the configuration model type, in which the result by Jacob and Mörters said that there was this critical parameter equals 0 before tau equals 4, and in the mean field version there was for tau smaller than 3. Now, in terms of our parameters, mean field, we're going to expect to see some behavior like it when eta is very, very, very large, right? So stars are updating like crazy. As I was saying before, when you take eta equal to 0, you recover the Jacob and Mörters result. And with eta very, very, very negative, right? You expect everything to freeze and to see something like the static network. Now, since we are looking only at the case eta positive, right? What we will try to do is to see if these two are seen by our model. Okay, so what is our main theorem? I'm not going to give the theorem in full because it's long and it's unnecessary for a presentation. So for the configuration model type with this kernel, we have, okay, before we were plotting everything against tau, but now we have to include the new parameter eta. And what we have here is the following graph, in which you have slow extinction in this region over here and going to infinity, right, vertically, and fast extinction over here. And if you localize what were the results for the mean field version and for the Jacob and Mörters version, you have this. And interestingly, when you reach eta equal 1/2, you are already seeing what happens at the mean field model, right? So you don't actually need eta very, very, very large to see the mean field model behavior. Okay, actually, our result is much richer than this, but for me to just to show it, I need to talk a little bit about the proof. Okay. Sorry, I just need to, okay. How do we prove slow extinction? We know that the infection survives around stars. And what we're going to do is to look for strategies used by the infection to spread between stars. This is the main idea, to just find how is the infection going from one star to the other, because now we don't have exponential survival. So these flares that you need are going to be, you don't have enough time to see them. Sorry. Okay. Okay. Now, each strategy that we are going to look is going to impose a minimum degree for the stars. So we need stars to be at least as strong as required by the strategy to ensure how the viability of the strategy. So what we're going to do is to separate vertices between stars and connectors. So stars are going to be the vertices from 1 to AN, right? And connectors between AN and N. And A is basically some new parameter that we are free to choose to select how strong we want our stars. And importantly, stars have degree A to the power -1 over tau -1. Okay, this is very important now. If several strategies are available at the same time, I haven't talked about strategies yet, but if several strategies are available, then we can talk about the most successful one. So what is the most successful one? The one that is giving you the largest density of infected vertices, right? This is going to be metastable density. So what will happen is that the contact process is going to stabilize. The density of the infected vertices in the contact process is going to stabilize around some value before quickly dropping to 0 on the extinction event. So the metastable density can be defined, computed, as A to the power 1 minus 1 over tau minus 1 times lambda. And this is just basically saying you have a proportion A of stars, each one of them have this amount of neighbors, and you have lambda times this amount of neighbors infected. So you compute the product and you just get the metastable density. Now, this is the first proposed strategy. Delayed direct spreading. So what we're going to say is that stars are going to uphold the infection for a very long time until two stars are directly connected, and then they're going to infect each other. Right? So this is direct because the vertex directly infects the other center. And in a time scale of order local survival. Now the heuristics, okay? So how many stars does a single star infect before recovering? You just take lambda times the amount of neighboring stars, right? Times how long this is going to be infected, right? And this you can compute. You just take lambda times TL and the amount of neighboring stars you can compute with this integral, right? Because this is part of the kernel-based approach. And then you can compute the number, depending on A. And now you want to impose a replacement equation. This over here, okay, if you simplify it, you obtain this expression, and you want to say this is equal to 1. So every star that becomes, that recovers, before recovering, infects another star. So this is enough to guarantee, at least at the heuristic level, that the infection keeps going forever. Now, of course, if you look at this, because tau is larger than 2, this is only positive if this is negative, because you have this lambda cube, which is going to be something really, really, really small, and you have to take A, which is something between 0 and 1. So you need this negative for this to balance this lambda cube. And the other thing is that you need eta to be smaller than 1/2, because otherwise you don't have local survival. You need eta smaller than 1/2 to see local survival. Okay, and you can compute the metastable density, and this is all the information that you need for this strategy. And of course, this is only a heuristic proof. The real proof just is much more delicate. You need to construct events that are recursive and that each one potentiates the other. It's a much more complicated proof than this. Okay. Now there is another strategy, which is quick direct spreading, which is basically the same, but you don't ask the infection to wait for long. You just wanted to do it in a time of order 1, which is the time at which you see the very first infection recovery event. Okay, you can repeat the same heuristics. So how many stars does a single star infect? You just take lambda times the neighboring stars. Now you don't multiply it by the local survival time, and you obtain some expression, and you impose the same replacement equation. With this, you just obtain what are the things that you need, in this case, tau smaller than 3, and you obtain a metastable density. Okay, just let me check how much time do I have. I have like maybe 8 minutes, something like that.
Yes, 8 minutes.
Okay. Okay, so I'm just going to quickly say that the more complicated part of this proof is to obtain, is to show that there are no better strategies or that the infection dies out. And this is done using a super martingale argument in which we construct another system which we couple, which is a little bit more resilient. And what we do is we define a super martingale and define a scoring. It depends on a scoring that in which we ask it. For instance, okay, so the scoring represents what is the infective potential of a vertex. So if after infecting whoever is going to be infecting in average, then this infecting potential decreases in average, then of course we are going to see a decrease of the infection until it reaches 0. I'm going to skip this one, but this is just going to give us upper bounds, matching upper bounds for the expected the expected density. Okay, now we go back to the picture of the main result that we found out, and actually we can say a lot more. We can say when it survives, what is the most successful strategy? What is the optimal strategy for the infection? So you can see here a region in which the optimal strategy for the infection is quick direct spreading. So you just directly infect other stars on a time of order 1. However, in this triangle here, what we show is that there is delayed direct spreading. You need, okay, so above 3, you need to wait for some time. However, here in this region over here, it's actually both of these strategies are available at the same time, but delayed direct strategy is more is optimal. And in the a byproduct of our proof is that actually when there is fast extinction, we can split this region into 2 regions. One in which there is ultra fast extinction, in which actually the extinction time is logarithmic, whereas here is polynomial. Okay, now I said that there were 2 kernels. Okay, one was the configuration model kernel, and the other one was the preferential attachment kernel. For the preferential attachment kernel, we also studied using the exact same techniques, and we obtained this picture over here. So here, notably, below 0.5, right, what you find is that there is always, you have an infinite region over here in which the critical parameter is equal to 0. However, when you reach 0.5 and you go upwards, then you are again as in the mean field model. And we can split this, we can split this picture again into regions. However, we can see here that there is an I, as opposed to here in which just there was quick direct spreading, delayed direct spreading. Oh, sorry, it's IDS, not DIS. So there is here, these 2 new strategies are quick indirect spreading and delayed indirect spreading. So what are these new strategies? Well, it's just the same thing as before, but instead of directly infecting one star, infecting another one, you just use an intermediate step using a connector. And this is, it makes sense for the preferential attachment kernels in which usually stars are not really connected one another, but they are just connected through intermediate vertices. You can do the same heuristics, obtain what are the density of the infected vertices, as well as the conditions, and you just consider every single strategy so far, and you just decide which one is optimal. Okay, so since I have not much time, I'm going to just quickly address what are the new results. This is what happens when eta is smaller than 0, in which everything is starting to freeze. So the local survival acts a little bit different, and this is the reason it took us so long. Okay, first of all, you need to understand local survival in the case eta is smaller than 0. You first need to go through edge updating, which of course not going to something that we'll be covering today, but except for this. So in the edge updating case, what you see is that edges are the ones that are now updating. So what you're going to be seeing is that you lose your neighbors one by one and replace them with new neighbors. So what will happen, so these updatings, you can see them as recoveries. So basically what you're seeing is that there is a contact process with some recovery and some additional recovery on top. So you can think of it as recovery rate 1 plus kappa xy. So if you renormalize, you recover a contact process with this infection rate and recovery rate 1, and then you are just as in the static case. So you just want this renormalized infection rate squared times the expected degree to be large. And in that case, depending if eta is positive or if eta is negative, then you recover different expressions. But the important part is that this survival time is exponential, as opposed to the previous case in which it was linear. Now, when eta is more than 0, you see two time scales. A time scale of order 1, in which you see edge updating, because the stars are mostly frozen. So all the surrounding vertices are the ones that are updating. And because the ones that are updating, because these vertices are updating, it's the same as if the edge was updating. So in the time scale of order 1, what you see is basically edge updating. However, in the time scale of the updating of the network, of the central vertex, of course, you see center updating. So you can see here, this is what happens. Usually you just evolve as usual until the central vertex updates, you lose every single neighbor and you replace them with new neighbors, which are, of course, healthy. If you look at now the timeline, now the amount of events is reversed. You see a lot of recoveries and some updatings once in a while. I'm going to just finish very quickly in 2 minutes. Really sorry. Okay, so now if you let the center to just evolve, the start to evolve in time, it's just as in the static case, until you face an updating event, in which case what you need is to either reach it infected, right? Or no, in which you need to face it infected and then infect everyone else very quickly again later on. So the possible bad events. Possible bad events is that you reach the updating healthy. I'm talking about the center, or you reach it infected, but it quickly recovers after updating before it had any time to infect anyone else. If you take into account everything here, the probability of surviving an updating is this one. And of course, this is just going to be a geometric random variable, the amount of times that you can survive. So again, what you find is that the local survival time is not exponential, but linear, right? And here you have this lambda square expected degree times to the power of 1 minus eta, which is somewhat different than before, in which there was 2 eta. But the reason that is different is because the nature of what is happening is varying. Okay, I'm going to skip the main challenges. I'm really sorry, but I'm just going to say what are the main results. For the configuration model, now the full picture is this one. If you take eta above 0, then what you see is what I showed before in the previous picture. But now if you take eta smaller than 0, now you have this rich picture over here. Okay? With which is okay. So I think one of the most interesting aspects of this picture is that every single difference between region, the change in colors are differences in the exponents, but these are the same strategies, the ones that are optimal. But every single change is given by a straight line, which is something we don't really understand why. And most importantly, when eta goes to 0, what you see is that between 2 and 2.5, you have this red region, and above 2.5, you have this dark green region. And this is similar to a previous result in 2011 by Mountford, Balsin, and Yao, in which they found the metastable densities for the contact process in the static network. And between 2 and 2.5, the exponent is exactly the same as ours, and above 2.5 is exactly the same as ours. So this gives us confidence in saying, well, when eta is tending to minus infinity, what you recover is actually the static case. And when eta reaches 0.5, then you recover the mean field scenario. And what happens with the preferential attachment kernel? Okay, when eta is above 0, then you recover the previous picture. And when eta is more than 0, then you have this slightly less rich picture than the one before, but still interesting. And what is important here is that no matter how big, no matter the value of tau, you have slow extinction, right? And you have this dark green region, which again is the case in which you have the exponent 2 tau minus 3, which is something that Van Houwekant proved in 2017 for the metastable density of the configuration of the preferential attachment. Okay, I'm really sorry to take so long and not covering everything I wanted to cover, but so of questions. What is the behavior at the boundaries of the fast extinction region? This is something that, of course, we haven't looked at. Other possible kernels with new strategies. Other possible stationary dynamics that we could cover with our techniques. And of course, a very different direction is to consider the geometric version, which is something that is being done, has been done partially with this random connection models by the probability group associated with Peter Mörters and his postdocs and PhD students. So thank you very much.
Thank you, Amitai. Questions? Comments?
You have a question?
Yeah.
So it's about the dynamics of the dynamic scale-free network. So how is the what do you know how the mixing of the dynamic of the dynamics depends on the on your parameter on your parameter theta?
You're talking about the mixing time, for instance, say for a random walk or something?
I'm saying, okay, so you can think about the evolution of the graph as a Markov chain on the state on the space of graphs, no?
Yeah. It shouldn't take long, because as soon as every single vertex has updated, then you're already mixed. The same happened with the edges.
Mm-hmm.
So it shouldn't take long, actually. And there's also for the contact process, at least when lambda is very, very close to 0, you don't really care much about the mixing of the non-stars. You only care about what happens at stars, because the infection dies out really quickly on the connectors. So I think that this should be the thing to study.
Yeah, I was thinking because there might be an interplay, no, of the mixing of the underlying dynamics,
Yeah,
and the behavior of the contact process. So it's like you know, there are these works on cooling environments where they try to bridge these two things, and it seems that those type of numbers may have a. I mean, maybe it's something to look after. It's another parameter, no, that might be interesting.
Perhaps I haven't really thought about it. Okay, so my intuition is that so the mixing is actually something that it's going to be like it's going to be hindering the contact process. This is something that I didn't talk about because I didn't have the time. But okay, so there's a phenomena that's the reason that it took us so long to complete this paper, which is a depletion effect. Okay, so the thing is that when you consider direct infection between stars, right? The edge between stars tends to become static, frozen, right? So once a star infects another star, then you just don't really care about this edge. So it's like the edge disappears in a way. And we consider here is that the infection in this case now is spread not at rate lambda, but at rate the updating rate. And this comes to me as the only real scenario in which the mixing time could play a role, other than just destroying the local survival. And something that okay, so this depletion effect, now that I talked about it a little bit, is the reason why this yellow part, the delayed direct spreading changes its color, and then it's replaced by another strategy because of this depletion effect. It's becoming less effective until some other strategy becomes more optimal, which is part of the richness of the picture.
Okay. Thank you.
I also have a question. You can understand the parameter eta as trying to make the dynamic model richer, so that it can, for example, approximate the mean field or the static case by varying eta. Have you considered doing the opposite, introducing more richness to the mean field model, so that it, by varying some extra parameter there, you can mimic the static case?
Oh, no, we haven't ever thought of that. That's a really interesting approach. Okay, so this is very far from my zone of comfort. These are very different techniques because these are systems of infinite system of ODEs, but perhaps there's another way of approach the static case to the mean field. Nevertheless, okay, so my guess in that case is that if you wanted to reach the same conclusion of the static case with the mean field version, my guess, totally just off the top of my head, would be that you would need to introduce like infinite richness.
Okay, then you can do basically everything.
Yeah, because in some way you would need to just store the whole information of the graph in order to have local survival and the infection between stars.
I see. Thank you.
Yep.
Sorry, may I ask another question?
Yeah, sure.
It's so now that I also mentioned the mean field, the mean field equation. So, do you converge to the mean field equation in some sense? I mean, convergence to not only in the sense of global parameters, but the equation itself. I mean, if you look, let's say, you look at the number of, I don't know, at the density of infected vertices with some degree, something like that. Do you converge to that equation?
I mean, we haven't proved it, but I think that it does. And let me go back to the definition of the model, right? Okay, so in the definition of the model, every single vertex, every single pair of vertices is connected with this probability. right? So if you let if you let the speed of the environment to go to infinity, then every single vertex, every single pair of vertices is actually connected with this term multiplying the infection rate lambda, right? And as n goes to infinity, then you should recover the equations, just as here. So I think that there is convergence of the network towards the mean field equations. Did I answer the question?
Yeah.
Oh, okay.
Amitai, just a quick remark. I remember that Enrique Angel talked about the joint work with Leo Rolla, where they were considering the one-dimensional, the contact process on the one-dimensional line, on the line. And they had some, I don't remember if it was just one or more sites which were spreading the disease faster. Have you considered this? I mean, instead of scale-free networks where the infection rate is not homogeneous?
Okay, I'm really sorry. It just came out the audio very cut, so very metallic. I could just understand some parts of the question. Can you repeat it, please?
I mean, to make it brief, networks, I mean, you look at graphs, not scale-free networks, but just more regular graphs, and the rate is not homogeneous. So instead, you have sites which spread faster.
That spreads. So the question is, if we have considered networks which are not scale-free but which are not homogeneous, this is the main question. Huh? Sorry.
Sites which get infected faster. Would you?
Okay. No, we haven't considered it. So basically, it's not. You would consider like perhaps there are like vertices which are more susceptible than others to infection. No, we haven't considered. This would be. Yeah, I think that this could be something that perhaps some of our techniques could handle, but we haven't looked into it. Just the regular contact process. But yeah, this is a very interesting idea.
Okay, I think we can stop now, and if there are any more questions, you can write to Amitai. Okay. Okay, see you next week.
Okay. So thank you very much.